In the last lecture, we started looking at how strings are stored in memory. I'd like to take a look at how integers are stored in memory and how to print out the actual addresses of memory locations. So let's copy .c to memory.c. Let's edit the file. Get rid of some stuff that we don't need. I'm going to declare two variables, I and j, integer variables. I'm going to let I equal 5 and j equal 2. Print those out. Let's compile that and run it and make sure that's working. Alright, everything's fine. But now I'm interested in the addresses of I and j. Where are they stored in memory? Well, if you remember, we denoted ampersand I as the address of I and ampersand j as the address of j. We can print out those values. Using the :T notation in printf. The reason why it's P is in pointer. Remember that I said ampersand I is an address, and it's also considered to be a pointer. I have a little typo there. Let's fix that. So I'm getting the address of I and I'm printing out that address. I'm getting the address of j and printing out that address. Let's compile, run, and what we get is rather interesting. Okay, address locations are printed in this format. The 0x means that the rest of these characters are in hexadecimal. For those of you who don't know hexadecimal, that's base 16. So in decimal we have digits from 0 to 9. In hexadecimal we have digits from 0 to 9 and then A, B, C, D, E, and F, where F is 15, in the way we would normally think about things. Okay, when you buy memory, you get, let's say, 4 gigabytes of RAM. That's gigabytes. So every memory location stores 1 byte of information. So if we're going to go from F8, which is the first byte for J, to FC, which is the first byte to store I, how many bytes are taken up by J? Well, it's F8, and then F9, then FA, and then FB. 4 bytes are being used to store J. Well, a byte is 8 bits. We have 4 bytes, that's 32 bits, and that makes sense. That means that an integer is stored in 32 bits of memory. And that's precisely what we learned in an earlier lecture. Okay, another thing we can talk about here is how many hexadecimal digits are there? Well, there's 1, 2, 3, 4, 5, 6, 7, 8. Alright, each hexadecimal digit represents 4 bits. 8 times 4 is 32 bits. And that means we have 4 billion memory locations. And that's again consistent with the idea of buying 4 gigabytes of RAM. Or putting it another way, it's consistent with having a 32-bit machine. 32-bit machine means that we can access up to 4 gigabytes of memory locations, but no more. So that's why we have to buy things like 64-bit machines in order to access more memory. We can only access 32 bits of memory with this notation. Okay. Now suppose I want to access what's in those memory locations. Equals, we can sit there and use star, I equals %d star ampersand I, and same thing with j. What are we doing here? We're saying we have I want the address of I, and then I want the thing that's at the address of I. So that's I again. We have j, the address of j, and the thing at the address of j, which is j again. So this is convoluted notation. We would probably never want to use it, but it does make things a lot more understandable to see what's going on and what the relationship is between the address and then the star notation. Okay, let's conclude that lecture.